All right, thank you for hanging in there for the end of the second day. In this session, we're going to shift the conversation a little bit. So the last 2 days we've been talking about technologies for CDR, for MRV, to deal with the climate change. But in this session, we're going to talk about the here and now, the acceptance that climate change has changed things in coastal communities and needing to find tools and technologies to deal with that in those frontline communities. And so our panelists here today are going to talk about ways in which they've come up with solutions for technologies and co-designed research with those people and communities that are actually going to be using them, because that is incredibly important, as you can imagine. And as the last panel discussed, the needs for this and the needs for adaptation. So first off, I'd like to present our first speaker, Jose Rolando. He is a PhD student at Georgia Tech.
Thank you very much. I'm going to be talking about this specific case study that we have been working on in Charleston for the last at least 3-4 years already. And our project is really, we leverage a very diverse team of people, right? Scientists from Georgia Tech. We have also the DNR, the local agents there in South Carolina, engineers from Charleston as well, the aquarium, of course the community, which is very important as well, and the University of South Carolina. And we're studying these salt marshes, so wetland ecosystems that experience sudden vegetation dieback, as you can see in the picture, right? Everything that you see there as mudflats used to be once a marsh. So vegetation dieback events we know are increasing in frequency in the last 25 years. And these events are these are characterized because large areas of vegetation just die off within short periods of time. And previously it was thought to be a transient event. However, we will see now that actually that's not really true, at least not for our case study. And as I said already, it's been increasing in frequency in the last previous years, right? So then in our study area in Charleston, we noticed that starting in 2013, you can see here in this progression of imageries that there was a step dieback here, especially in that cup down here, that has not really progressed or came back to life in the last few years. So our question then was, why was this happening? So what's the cause of this? And what were the characteristics of this ecological event? And the second question is if we were actually able to restore these ecosystems and how. So to do this, we used a combination of remote sensing data, field analysis, and statistical and GIS modeling. I'm not going to go through the details because of time, but we can chat about it afterwards if you want to. But we use multispectral imagery just to characterize the vegetation, digital elevation models to assess how well the marshes are doing in relation to sea level rise, and then we verify that in the field. So what we found out is that if you see those maps there in the right, we calculated the areas of the marsh were vegetated or unvegetated, and you see an increase on unvegetated areas in purple since 2013, and you can see that also in those bar plots there in the top here. And you'll see that starting in 2013, as I said, the dieback started, and that coincided very, very nicely, well, not nicely for the marsh, but at least for the statistics, right? There was there was an extreme drought in 2012, 2013, 2011 that then caused this dieback event. And then we saw a second spike in 2016, 2017 that we think was influenced by Hurricane Joaquin, which caused a historic flooding in Charleston. So the main point here is that we know then that these dieback events are caused by extreme weather events that also we know that are going to be increasing in frequency and intensity because of climate change, right? And then we also know that in this case at least, this was not a transient event, but it's been at least impacting this ecosystem for some time already. Second thing is that these dieback events were associated to marshes with lower elevation, meaning that they are more ponded and they have less hydrological flux. And also with areas on the marsh that are in the what we call the mid-marsh or interior of the marsh, so that it doesn't really have a lot of, again, tidal exchange because they are farther away from the creek banks. Good news, though, is that we can restore these marshes, and you can see this is actually being driven by the South Carolina DNR, led by Michael Hodges and his team, and enabled by the community and volunteers that have been going there since 2019, planting grass, Spartina grass. And we show that after 2 years, the biomass of these planted or restored salt marshes are very much the same as reference sites that were not impacted by dieback events. So that's good news. And then we have actually restarted a new phase of restoration in which we're actually now performing active restoration of this site in a larger scale. And what we're doing now is we're creating new tidal creeks to improve the hydrology and the exchange of nutrients and pollutants and whatever there is in the marsh with the surrounding estuaries. So this just happened 2 weeks ago. This is very preliminary, well, it's not data, but at least evidence of what we are doing there. And that's going to be also being coupled with what we know is already working, so more grass planting, and we'll also be doing more oyster reef habitat creation in order to stabilize the newly created tidal creeks. A lot of that information you can find in this paper is going to be published, I hope, in a couple of weeks. It's in press, in Ecosphere, and that's it for me. Thank you.
Thank you, Jose. Our next speaker is going to be joining us remotely. Delphine Lobel from Fugro. Can we bring her up on the screen, please? What? Oh, I'm sorry. Our next two speakers will be joining us remotely. The next one will have Benjamin Hamilton, yes? Is that the next? Yeah, okay, great. Sorry. Yes, thank you.
Okay. All right. So yeah, thanks for giving me some time to speak here, and apologies for not being able to join in person. So today I'm going to talk about a new satellite that we have launched at NASA, fairly recent. So it's December of 2022. Sorry. I think my timing's going to go. Okay. So it's a satellite we launched in 2022. It's a brand new satellite, and it's really going to support improved information about coastal sea level. So I'm excited to talk to you about it today and just give a little overview of what it can provide. And I should introduce myself. My name is Ben Hamilton. I'm at the NASA Jet Propulsion Laboratory and also team lead of the NASA Sea Level Change team. All right, so looking back at how we have measured sea level from space, we have what we call the conventional satellite radar altimetry. It's a long track nadir pointing altimeter. So basically what that means is it measures the height of sea level directly below the satellite, and it covers the Earth every 10 days, providing these measurements. We kind of filled in some gaps there, but we get these measurements. They're pretty accurate. Just to show you on this next slide here, the measurement principle is really, it's simple. It sends, the satellite sends a radar pulse down to the surface of the ocean, and it times how long it takes for that pulse to get back to the satellite. And from that, and doing a bunch of environmental corrections, we can get a very accurate measurement of sea level from space. And we can actually get a measurement of an accuracy of about 1 inch. So again, a pretty impressive measurement of sea level from up in space. And here in this video, which we'll play, you can get a sense of how it's measuring. So this is the most recent in the 30-year record of satellite altimeters that we've had, the Sentinel-6 Michael Freilich, which was launched in 2020. And you can see these measurements that are being made. A couple things to note here, and what I want to talk to you today about is that there are gaps in these measurements. So you can see gaps in between those ground tracks, those tracks that the satellite is making over the surface of the ocean. And also as we get closer to the coast, the satellite really cannot measure directly at the coast because of how it sends that radar pulse down and how that radar pulse interacts with the land and ocean at the interface. We can only get to about 10 to 15 kilometers up to the coast. So we're missing a lot of really detailed information right at the coast that's really important. So a solution here, so I'll pause this for just a second, is was launched in December of 2022, so just end of last year. It's called the Surface Water and Ocean Topography, or the SWOT mission. And this is a different type of measurement. So it's still using a radar pulse, but instead of measuring a long track directly beneath the satellite, it's actually measuring in a swath. So it uses this new Karen, so this interferometric altimeter. It sends these pulses down, and it measures these swaths that are about 30 miles wide on each side. So there's two 30-mile swaths. You can also see that middle, that bouncing red dot there. It does have a nadir pointing altimeter as well, similar to our older ones. But now we get this nice measurement of sea level going through time in this swath. Okay, so it's measuring the height of sea level in 2 dimensions now. And if we look at how this has changed over time, so this is basically what the ocean looks like using different altimeters in the past. So if we go all the way back to CSAT in the 1970s, you can see the ocean looks pretty blurry. GeoSat was launched in the 1980s. You can see a little bit better definition. Then with our reference missions, so the Jason series, which Sentinel-6 was a part of, again, you're starting to see finer and more detail as you go forward. But then with the SWAT mission, you can see the level of detail that we're now able to get within the ocean. So we're measuring resolutions down to 10 to 15 kilometers, so really small scale features in the ocean. And more importantly, we're measuring right up to the coast. Okay, so we no longer have this coastal gap that we had with the conventional altimetry. We're able to see both the smaller scale sea level signals that we know exist in the coastal areas, and we're able to get those right up to the coast. So it's really this dramatic improvement over time, pushing to smaller spatial scales and closer to the coast. That's really the evolution of these satellite measurements of sea level as you go through time. And just to look at this one other way, these are all simulations. Again, the satellite just launched, but this is what this SWAT satellite would measure in the Mississippi Delta region. That's a simulated field there in the ocean, the swirling features. But again, you can measure right into the coastal areas. One important thing I haven't touched on yet is that SWAT can also measure features on land. So it measures all surface water on Earth, both ocean and land. Sorry, I got my timings from when I did the recording. But it measures the water that's on land as well. So we really do see that interface, and we see those different water bodies that are within that coastal zone, which is really important for tracking the movement of water between ocean and land, and being able to track some of the flooding events that we know happen in these coastal regions. Okay, so what does this mean if we look at it in terms of the sampling we've had in the past? So all I've done here is take the number of sea level observations from space we have at different times in the past. So on the left there, you see just a given month in 2008. This is April in 2008. We had 3 satellite altimeters, ENVISAT, ERS-2, and JASON-1. You can see that you have a lot of gaps in the ocean, a lot of areas that are not covered. If you go up to April 2022, we have many more satellites that are up there measuring sea level, but still you have gaps. You're not getting that close to the coast. You have, let's say, on the order of 5 to 10 observations within the course of a given month. Now, if we add SWAT in on top of this, so this is what we have now. So this is that April sampling plus SWAT, or you could just take the most recent month. You can see how much SWAT is filling in the gaps in sea level and how many more measurements it's giving. So with that swath measurement, it's just giving us almost an order of magnitude more observations in the ocean. We're able to see not just finer scale, spatial scale features, but also see them more frequently in time. And just to finish up here, this is just came out a couple weeks ago. This is what we call first light from the SWAT satellite. So these are the first observations. Everything up to this have been simulated data that I've shown you. This is actual measurements from SWAT off the east coast of the U.S., off North Carolina there. And you can see a couple things there. One, you can see that SWAT is covering across the Gulf Stream. You can see that those dots in the middle, that's the nadir altimeter that SWAT has that fills in that gap between the swaths. But you can see that we're already starting to pick out these spatial features, these smaller scale features in the ocean, and really getting these rich measurements already closer to the coast. This is just in a certain orbit right now with the SWAT data. We'll be able to get even closer to the coast and see that interface once SWAT shifts to its science mission and its science orbit. This data is going to be available later this year, but the way that we're going to use this in order to generate better products in the coastal area in terms of measuring sea level is to integrate it with all the other observations we have. So I showed you we have all these other satellite altimeters that are up there. SWAT is going to complement those observations. It'll be used to improve models along the coast. It'll be able to measure flood events directly. So it's space-based observations on a global scale of flooding events that are occurring. So it's really just going to open up a whole host of opportunities for us to look at sea level in these coastal zones where it's really most important to understand and where we've really had a gap in our understanding to date. And with that, I will leave it there. Thanks.
Thank you very much, Ben. Very exciting era opening. Okay, so now we continue with Dr. Lobel, Dolphine de Lobel from Fugro. She's responsible for coastal resilience as a program inside Fugro. Lobel, are you with us? She's up. Oh yeah, she's. Hello?
Yes, sorry. I just need to first unmute and then share.
Thank you.
Okay. All right. Can you see it?
Yes, looks good.
Okay, perfect. So hello everyone. Yes, thank you so much for inviting me. And I'm so sorry I can't be there. I would have loved to be there in person. I'm calling in from the Netherlands. As Nadia just mentioned, I'm at Fugro, and I'm product owner for coastal hazard analytics, and we're working on digital twins for coastal resilience. So I will walk you through our vision and our mission, as well as showing you an example of one of our pilot sites in Palau in the Pacific. And then I will go through a little bit of the collaboration that Fugro is having with the UN Ocean Decade programs and what we're planning to do in the future. So our vision is to deliver data-enabled decision-making in the coastal zones. And we have three different solution spaces. One is on communities, the other is infrastructure, and then nature. So we want to understand how these coastal hazards can impact people, both the fast and the slow onset hazards, as well as looking into the coastal infrastructure and how we can have ensure that there are safe and resilient infrastructure. Finally, for nature, it's understanding the and managing the natural capital and nature-based solutions. And all of this is in order to enable the planning, the monitoring, and the acting towards coastal hazard preparedness. And as you can imagine, we're really focusing on decision makers, as you know, the community, so those that are representing the coastal communities. We're focusing on three different hazards, so coastal flooding, coastal erosion, and contamination and habitat degradation. So these are globally reaching hazards, and we're looking at how there are locally compounding impacts and that are obviously increasing in intensity and frequency with climate change. Our mission is to, as you know, I've been really intrigued by all of the previous talks in this session, and hearing how co-creation, co-development is really now a very common practice. And at Fugro, we are very committed to doing the same. So really looking at all of the different stages of what co-creation looks like. So starting off with the end users and understanding their challenges, moving on to discovering what their needs are specifically for their local area, as well as their specific needs depending on the stakeholder. Then moving on to exploring possible solutions, the technical and digital solutions that would work for them. And this is an iterative process where we do rapid prototyping and being able to have an interactive environment with the end users where we rapidly test ideas. And this can be 1 week to 2 months. And we have a digital lab that we call Virgio and that we use for this process. And finally, this enables us to deliver a tailored solution to meet the specific needs of the end users. So Fugro is at the heart of Fugro's innovation and technology. So we want to be able to explore technology that help us to deliver remote and autonomous data. So for the last 60 years, the legacy of Fugro is acquisition of geodata. So acquiring geodata from all around the globe and being able to integrate it And it can be from crowdsourcing, satellite data, autonomous, in situ, etc. And then for all of the in situ instruments, we are developing this edge to cloud, smooth transition from the field to a solution environment, and working on this near real-time live streaming of data into this the digital solution. The platform that we are working on to integrate and visualize the multi-source geodata is Vergeo, as I mentioned, and this also includes in-house models that we work on: hydrometeorological, morphodynamic, river modeling, and obviously integrating open source data too. And finally, delivering advanced analytics. So through the use of artificial intelligence, machine learning, we can integrate, we can use artificial intelligence on these integrated data sets and provide some advanced analytics for the end users. And this can be risk analysis, for example. It can be understanding the impacts, the socioeconomic effects, for example. So, we're really looking at what that end user is really needing to obtain which information. I'm now going to show you a video of one of the pilot sites. So we have quite a lot of work that's in the Pacific for the low-lying island states. And this is an example of Tuvalu, where Fugro worked with the UNDP. And I'll just show the first minutes of this video.
In the Pacific atoll nation of Tuvalu, communities live right on the doorstep of an ever-changing ocean, at serious risk from cyclones, rising sea levels, and storm surges. In order to put effective adaptation methods into action, the Tuvaluan government requires accurate mapping of their surrounding coastline and nearshore areas.
In 2015, the TC-PAM, which devastated our coastal frontier and had huge storm surge washing ashore and damaging a lot of infrastructure, buildings, and our crop plantations.
So if we don't understand the problem to begin with, it's very hard to come up with the correct answers on how to fix it.
The Tuvalu Coastal Adaptation Project, TCAP, is working to develop innovative coastal protection solutions. TCAP partnered with Fugro, who used their airborne LiDAR technology to provide accurate coastal data to the team in Tuvalu.
If you'd like to see the full video, you can find it on YouTube. Okay, so once we have this data acquisition component, part of the process done, then this is where we integrate it into the platform. And here I'm showing another island, Palau, where again, the UNDP are the end users and represent the Palau government and the coastal community. And we aim to have 4 digital labs in 4 different locations around the globe. And these can be locations where they have very little data, for example, available, and where we can help them to acquire the data, or other areas where they have a lot of data already available and they have very specific needs with, the next step in the specific information or analysis that is required. And this is to show what the final end product could look like. So in order for it to be, a digital twin, we definitely want to add the temporal component to it. So this is something that is currently quite challenging, in the digital twin community, is how to have a 4-dimensional visualization. So here you can see an example of St. Martin in the Caribbean, where you have a flood event that is coming through. And as a final, you'll soon see that there are buildings that are turning red, for example, to show the risk to infrastructure. And the same can be done for, obviously, coastal communities or natural assets. And finally, we are working very, very closely with the UN Ocean Decade different programs. So Ditto, Digital Twins of the Ocean, we're an official partner. Coast Predict, I think you're going to hear a bit more about it. And Predict on Time is one of the core projects where they're looking at early warning systems. And so we're definitely collaborating on that regard. And our Fugro Cape Town office is very active in the Ocean Decade-Africa roadmap, and they're very concerned about the coastal resilience issues. We've heard quite a lot about it today already, so we're very excited to see how this can be, how we can collaborate further. And finally, Ocean Visions, of course, so Global Ecosystems for Ocean Solutions, GEOS, and yeah, I'm a steering committee member, and we're working on how Fugro and Ocean Visions or GEOS can work together in this space. So just a couple of key takeaways. We are working on coastal resilience efforts, and co-development is definitely the process that we are using in order to look for digital solutions for the end users. And this can include digital twins or other digital solutions that fit for purpose. And public-private partnerships. So obviously Fugro is a private company, and we are very much working towards how we can have a public-private collaboration with many different other public groups. And this is key for coastal resilience. Thank you very much.
Thank you very much. And now we go to Dr. Russell Clark from Georgia Tech. Let's see if I can make it this time. Probably yes. Thank you.
All right, thank you. And thank you everybody for being here at the very end of the day on a long day of sessions. We appreciate your interest and your support. I am Russ Clark. I am actually a computer scientist of all things, my background. So I come at this work from the sensor technology perspective. And I want to tell you a little bit about what we've been doing. Kate Morano in the previous session introduced a little bit about the project here in Georgia, on the Georgia coast. And I want to tell you a little bit more specifically about some of the engagement we're doing with educational programs, especially K-12, to make this happen, make this work meaningful and impactful here on the Georgia coast. So we're part of the Coastal Equity and Resilience Hub here, and we're going to talk about this effort that started several years ago to address this missing data link, the missing data set here on the Georgia coast, where basically when we would have flooding events, when we would have storm events, we often did not, we basically had no visibility real time into what was happening, what the water levels looked like over 100 miles of the Georgia coastline. So there's one NOAA gauge, Weather Service gauge, on the Georgia state line of South Carolina, and then the next nearest one, more than 100 miles away in Jacksonville. And so there was this big gap of us knowing what was going on, especially during flood events. So we set out to deploy this high density, hyperlocal set of gauges, monitors that were low cost enough that we could basically flood the area with them, no pun intended, with as many of these as we can, so that we can see what's going on at the local level, at neighborhoods, on bridges in the community, on roadways, what's happening to critical infrastructure. The project we've deployed more than 50 of these on the Georgia coast, many of them in the Savannah, Chatham County area. So for perspective, that's about a 200 square mile area. So this is a pretty high density deployment. Our first real use of this, how we got into this, was really looking at emergency response. So we have hundreds of bridges in Chatham County. The first responders wanted to know Can you tell me which ones have been impacted by rising water during a storm event? But from there, of course, a number of other activities, including resilience planning, community engagement, and the education piece, which is what I want to focus on today. A really important part of this has been the K-12 engagement, and in some ways, perhaps the most exciting part of it for me. The whole focus here is creating these equitable education opportunities for the youth that are living in this environment, dealing with increasing flooding. This is their home. We want to help them understand it, and we want to help them develop solutions for adapting and dealing with it. So everything from the development of sea level rise curriculum, for instance, working with some of our partners specifically focused at the middle school, 6th to 7th grade, but also the actual assembly and deployment of the sensors themselves. So one partnership I want to focus on is one of the high school teachers in Savannah that came to us very early on and said, I've got these students working on engineering projects. How can we get involved? How can we get the students involved in this work? So we worked together to develop and integrate into the curriculum the students actually assembling the sensors. We literally brought them a box of parts, and they did the soldering, they did drilling, they did assembly, they did testing, they dunked them in a water tank to make they were sealed, and then they basically helped us to prepare them for deployment. And this is a really, one of the misconceptions people will say is, wow, that's great, you have free labor building your sensors. Actually, no. I can assure you it would take a lot less time if we just built them ourselves, right? The time invested is in developing a program with the teachers, being there with the students, working through the semester long project where they actually have this real learning experience. And so these are, this picture is one of my favorite on the upper right. This is where the students have actually signed the ones that they've built. So still to this day, when we go out and service them, we see that. And just to be clear, we're working with NOAA and Socorro here. These are intended for, and at the installation time, these are sort of first-rate sensors. We invest in surveying them to get the elevation. And so these are, production sensors when they're deployed. But we have interest from the community that basically goes beyond that. These are relatively low-cost sensors at the $500–600 point, but we have people that actually are asking us for much more than that. Even higher density. What's going on in my park, right, and the drainage systems around my house. And so, as Kate was talking about from the community engagement side, when the community members come to us and say, hey, we have these additional needs, part of what we want to do is work with them not just to figure out how to deploy more of these sensors, but actually go another level into actually developing them and creating learning experiences around actually designing new sensors and figuring out how to apply that in their local communities. So, and it's not just water level. These are some examples of rain gauges and air quality and soil moisture and soil temperature and all the other things that might be relevant in the flooding that's happening in their playgrounds and in their parks, and working with those community members to develop after-school programs, weekend programs, summer camps, where students come together, design, build something that they're going to deploy in their own neighborhood, and then learn how that data can be useful to tell the story to hopefully help get some solutions to these problems that are affecting them in their daily lives. So that's also a really important part of it. that's our story, and thank you.
Okay, so we are now at the last presentation. Dr. Giovanni Coppini, he's the director of the Climate Center Ocean Application and Forecasting in Italy.
Good afternoon, everybody. It's really exciting to be here with you, and I will try to describe to you the activity that we are doing in our institute. As you have seen, is a collaborative effort. We are more than 60 people working on this activity at CMCC. So our main activity is, and our main challenge is to improve our modeling capacity. So we go across the global to coastal scale, as you see in the sketch, more and more using a structured grid modeling and reach the catchment and coastal scale up to the harbor scale. And then we develop application, or you can call them solutions, to that are, I'd say, user-driven or challenge-driven. So the dialogue with the users is very important. And we continuously try to improve the modeling and the application themselves through gathering user feedbacks and up to commercial exploitation. Our time scale is from the past, so we build up a reanalysis, short-term forecast, and then seasonal forecast and climate projection. Of course, we integrate as much as possible in situ and satellite observation, also gathering ourselves, especially through the data simulation and validation process. So the first example is this is work done in European project, but also in the Ocean Decade. I will mention the FLAME project at the end. We are trying to improve the climate downscaling. Our test bed is the Adriatic Sea, which is a very complex area with lots of catchment and rivers entering into the ocean. So our approach is to downscale first the atmospheric regional climate projection, and then downscale as well the hydrological component, and then force the different ocean component like ocean circulation, biogeochemistry, and waves, and then further downscale to the very high resolution coastal areas. So this approach is, I'd say, quite new in terms of integration and in terms of trying to catch up with all the complexity, especially, for instance, looking to the hydrological component. Here you see very simple pictures where we show the improvements compared to the regional already considered high resolution climate projections. So in green you see the Med-Cordex, and while our for the past period climatology compare with the Copernicus reanalysis, so what is similar to the truth, and our new climate scenarios, and the other example for the other variables. So I think this is the way. Of course, the next step will be fully coupled integrated Earth system model for the coastal area, but we are very happy with the recent results. And this activity is now put in the context of cost predict and the FLAME project. Here's some example of then how you, for instance, add value to the sea level rise in terms of coastal impacts, for instance, in the southern Adriatic Sea, in the Apulian coastal areas. Once we go to the operational forecasting, our approach is from the global ocean, as I was saying, to the coastal area, and I couldn't show a better example. This is the Savannah ocean forecasting system developed together with Georgia Tech and validated with the smart sensors network that we have seen before. These are, let's say, a capacity to increase the accuracy of the models, including, as you see, the possibility of enter inside the rivers, thus modeling the currents and sea level upstream, not only in the coastal areas. Yeah, this is an example of how the model is being used here you see the paper from Park, where you see that the high resolution model better forecast or represent the hurricane that was flooding. It was the Matthew in these graphics impacting the Georgia coastal area compared to the green model, which is the low resolution global model. So I wanted to combine in this presentation some solutions, let's say, for the climate change with solution for pollution and anthropogenic impacts. Here you see our Ocean system is a collaboration with a private industry called Orbitalios. In blue and red, you see the monitoring from satellite of the oil spill in Syria. We collect more than 30 images along the 20 days of a spill. It was a huge spill. And in gray, you see a 24 hours forecast based upon our modeling system. This is today a global to local oil spill monitoring and forecasting system because we can also use the high resolution modeling that you have seen, and is available for the entire global coastal ocean, mostly automatically. Here is an example of the evolution of the oil spill, first detected in blue and then forecasted. And of course, if you don't have high resolution modeling, that both atmospheric but especially currents model, you will never be able to project a forecast where the oil will go. You see how complex can be this type of a situation. Our modeling approach has been used also recently to start to plan ecosystem restoration activities. So here you see a cycle that we think is our interpretation of the digital twin. So we start from defining an ecosystem, in this case is Posidonia oceanica, and ecosystem services that we want to assess, like for instance sediment trap, but also CO2 uptake. Then we analyze the stressor, and then we plan what-if scenarios. So in this case, the what-if scenario is how to best model the siting and the optimal design of the restoration activity. Then we will progress and actively restore through patch techniques the Posidonia, but then in the meanwhile we will observe how the Posidonia will grow and how the ecosystem services will be, let's say, optimized or restored, and then we will improve back through this observation the models like in a loop, so similar to what is used, for instance, in aviation as a digital twin of aviation. Here you see the different phases that are already ongoing from the observation modeling experiments and then field restoration activity. Last two slides to mention that we have two projects, Predict on Time as a decade action, focusing on integrated coastal ocean observing and prediction system. We will have a workshop very soon in Italy, so please take note if you want to join. You're very welcome to come. And the second project is Flame, and it's about climate downscaling. And of course, you are very welcome to join Flame as well. Thank you.
Thank you. I believe Giovanni has to leave us to catch a flight. Maybe I'm reminding you at 6. Can you put up the other two speakers for us, please? Great. Did you want to ask questions? Yeah.
So we have a minute, and I was thinking what to do, and it came to my mind that to the people that are left here, plus the speakers following us remotely, we could ask a question, and if you could answer in few minutes what you think. And so the question would be, what are the major challenges for scaling up approaches that enable and advance community-driven coastal climate research and solutions? So let's start maybe with Ben. Ben Amlington?
Yep. Yeah, I mean, thinking kind of specifically from the satellite perspective, right? I mean, there is obviously, think about scaling up. I mean, there is a need to first scale down those satellite observations and bring them closer to the coast and put them into a form that is useful along with other types of assessments that are being made. So I think within NASA, within other organizations, there's a lot of work going into that to try to bring those down and deliver the data in a way that can be integrated into improved models. I think we heard some good examples of those types of models and the need to get closer to the coast and provide relevant information. So I think there's a lot of work to be done there, especially as we just start to scratch the surface of how these satellite observations can be useful and how we can take advantage of the global scope of the measurements that are provided. So it's not just that we can provide detailed information in one coastal location, we can provide that detailed information in every coastal location. So I'm not providing a great answer to your question other than that the additional work needs to go into finding ways to integrate that information with the work being done closer to the coast.
Thank you, Ben. And then we go to Lobel, please.
Sorry, I think my internet cut out just when you were asking the question. Could you repeat for me, Nadia?
So
Thank you.
What are the major challenges for scaling up approaches that enable and advance community-driven coastal climate research and solutions?
Yeah, I mean, I think I'm going to focus on the fact that there are some things that are open access and that, you know, could be provided to some communities that can use already very simple digital solutions. And, you know, having the links between actually, making them aware of these solutions. And also that, you know, scientists understand that low resolution, something that is quite simple, can already be very effective for some communities that don't have anything, right? Or are just relying on pieces of paper and maps. You know, this is what we understood from the Tuvalu example, for example. Yeah, they were, definitely on something using very, very basic analyses in order to prepare for these hazards, for example. Yeah.
Thank you, Lobel. And then we go to Jose, please.
I think in our case, at least, what was really important to be able to perform or start the restoration now is building a network of organizations and people to have all the skills and all the different type of tools that we need to answer first what is going on, and then to connect with the community and also to connect with the state agencies such as DNR, who are the ones who are actually doing the hard work in the field, right? And as well with the engineers that were actually developing the plan, and us, the scientists, who were asking the why questions and then monitoring and building then the knowledge also in order to inform future restoration events, right, or restoration actions. So I think for us was just just building the team, I think was really important, and and asking them, how do you develop that? I guess a meeting like this is a good example, right, in which you connect people from different disciplines, different backgrounds to get to answer these tough questions together. I'll say that.
Thank you so much. And then last but not least, Russ.
So the specifically with the educational component that I focused on today, it is a real issue that we have right now. It's as rewarding as it is for us working in the schools. There's only a few of us, and we can't work with every school, and we can't be in every classroom. And so we're actively working on looking at how do we develop curriculum, how do we work with education experts to develop curriculum and develop programs to package this type of activity and share it first with more schools here in Georgia and all along the Georgia coast, but also for consumption outside of Georgia as well.
Thank you very much, and let's applaud to all our panelists. Thank you, and now it's time to relax.